Welcome back everyone. I hope you had a good refreshing break and are ready for part 2 of the workshop. In this part I will show you how we analyze the CT sample which we segmented in part 1. More precisely, we will do a pore analysis in step 4.1 to 4.4 and a property prediction in step 4.5 to 4.8. This means that the goal of part 2 is that you will know the different functionalities of GeoDict for pore space analysis and property prediction. This includes pore size distributions, calculating open and closed porosities, and percolation paths. For physical properties, you will learn how to calculate the permeability, tortuosity, the elastic properties, and the conductive properties. Let's get back to GeoDict. I closed my GeoDict and started it again to show you what you should do if you closed your GeoDict for the refreshing break. First step, make sure that you are in the correct project folder as before. Second is you load the structure by File, Open Structure, and select the structure you saved. And if you did not save the structure we segmented, you can go to the demo data folder and select the structure which was written during the segmentation. Click Open, and the structure is loaded in 2D view. We now switch to the 3D view. And we select color and visibility on the right and change the red color of ID1 again to be white. We can close this window. And in camera, we can select the halo effect. And now we are at the same point as the people who did not close GeoDict. The first analysis we will do is heading to Analyze, Porodict, and do the pore size distribution. GeoDict has two options for the pore size distribution. One is the granulometry and the other is the porosimetry. The porosimetry is actually the same as the experiment where you have porosimetry by mercury intrusion, for example. But we will use the granulometry, which is a geometric approach to the pore size distribution. It is more accurate than the porosimetry. We select the granulometry and click on Edit. Here, please make sure that the symmetric boundary conditions are selected. They should be selected by default, but please make sure. We have to calculate symmetric since the CT scan is not periodic. If we later on create a structure periodically, we can calculate periodic. But for this case, stay with symmetric and make sure to check the right pore size distribution as GSD file. This is important to visualize the pores later. Click OK and run. Now GeoDict will start the granulometry to analyze the pore size distribution. This will take a few seconds since this is a pure geometric approach. And you see, we are already done in less than 10 seconds. When the granulometry is finished, the result viewer opens and you can view in the Results tab. You get the report, which lists the characteristic diameters, D10, D50 and D90, and also the geometric pore size distribution as a table. This table is also shown in the plots, but as a plot. We can also visualize the data by clicking on Pore Size Visualization, and we can load the pore size distribution file. If you cannot click this Load GeoDict Size Distribution, you forgot to check the checkbox. It's no problem, you can do that later on if you have the handout of the workshop, you can do it on your own again. We click Load Geodict Size Distribution and we click OK. And we see the structure with the pore sizes visualized in the structure. Blue means the structure's pore size is very low, and red means we have a large pore size. We can rotate the structure. We can also go to the volume field tab, and by using this slider we can clip smaller and smaller values away and only keep the large pores. Additionally, you can go to structure and clip through the structure in the different directions. And while you clip through the structure, you also can change the threshold. We change the structure back to normal, to be unclipped. And the next we analyze is the pore identification. For that we stay in the Porodict module and select the Identify Pores option. We click on Edit and now have a few settings to do. We select the minimal pore diameter to 20, so that not the single 1 or 2 voxel large pores are analyzed, because they might be artifacts which just harm our statistics. And what we also do, we leave this as it is. This option, remove pore fragments at domain boundary, removes the fragment at the boundary. This is important because the CT scan cuts through pores at the boundary. But since those pores are then half or quartered, are smaller than before and would ruin our statistics. So we just remove the pores to have the pure statistic over unharmed pores. We click OK and run. And now Geodict will identify each single pore and then make statistics out of that, and also orientations. This analysis is also done in a mere minute. And again, we are greeted by the result viewer. You see the previous results are still loaded until we discard them. And we see in the results a report. We get a number of pores, we get a contact between pores, we get pore volume percentage statistics, sphericity statistics, and more interesting, we get a diameter of volume equivalent spheres, or Geodict fits ellipsoids into the pores and can derive statistics, a mean value of the shortest diameters of the ellipsoids, or intermediate and longest diameters. Additionally, we get a direction tensor orientation of the pores. We can again head to plots and look at various different plots. Most interesting are, for example, the diameter distributions and the sphericities. And here we can also have a look at the identified pores. If we go to pore visualization and click on Load G32, which loads the pores as an index image. So in this index image, each pore will have its own number. Pore number 1, 2, 3, 4, 5, until pore number 17. Click on Load G32 and OK. Here we select No, because we would like to see the pores inside of the structure. We can see that the identified pores do not touch the boundary because we select to remove the boundary pores. If you click on this checkbox here in the top, you disable the view of the structure, and we can look at the pores we can rotate the structure by moving the mouse, and we can zoom by right-clicking and moving the mouse up and down. And we see that the pores are in fact rather elliptical and oriented. The next step, let us just show the structure again, is the determination of the percolation paths. For that, we again stay in Porodict and go down to the percolation paths and click Edit. The percolation path is the largest through path in the given direction. So Geodict uses a sphere and tries to push it through the structure, in our case in Y direction. So we select Y direction because it is the long direction, which is the more interesting direction. Geodict can also give you many different percolation paths. For this workshop we select 3. We leave the boundary condition as symmetric because again this is the CT scan. Then we click OK and run. In fact, in the background of Geodict you can see what it will do. It will find such a red path through the structure and give information on the length. We get information on the path length of the thickest path, the second thickest path, and the third thickest path, and the path length. We also can go to data visualization and select load result. This will load. It seems we have now loaded the percolation path into the G32 file. But that is no problem. We can just disable the view of the volume field by checking this box. And now we are only looking at the percolation paths and the structure. We can see how the paths are percolating through the structure. If you only want to look at the path without the structure, you can go to Color and Visibility and turn the ID1 invisible by just unchecking this invisibility box. And we now see the percolation paths, and in fact they are, in the end they are straight, but in the beginning they are going completely through the X and Z plane. This is an interesting analysis, and you get an even more interesting view if you click on Load Analytic Path. We want to see the ID1. We see now how the particles would travel through the structure on their way through the percolation path. To get a moving picture, we can play and see how the particles travel through the structure. Additionally, you can, and it's described in the handout more detailed, make a video following the particle through the structure. In this workshop I will only show you where you can find it, but we will not do it. If you click on this icon here, you get a mouse over text, and it will load a video dialog. This video dialog has several options which automatically creates videos for use. We have various presets. And here we have the follow particle preset. If you click on generate video, the preset will start to work. But as I said, more detailed information on how to use this preset, please look into the handout of this workshop. We will cut it for today. We click close. And we now go to the next analysis step. It's the open and close porosity. For that, we still stay in Porodict. Porodict is Geodict's pore analysis tool, so therefore the pore analysis will all take place in this module. We select open and close porosity and we click edit. Now we want to analyze the open and close porosity in attached to all X and Y directions. So this is the beginning and the end of the X direction, beginning and end of Y direction, beginning and end of Z direction. And that's everything we need to change. We click OK and we click run. And Geodict is again finished in a few seconds. All those pore analyses are finished rather fast because it's just geometric solving or analyzing the structure. While later the solving differential equations of the structure will take a bit more time. Again, we are greeted by the result viewer and get the open and close porosity. We get the overall porosity and the open porosity. And we see, okay, they are in fact different. We have very few closed pores. Closed pores are isolated pores. Pores that are not connected to other pores which are connected to the inflow or outflow plane. We can also visualize those open and closed porosities by clicking on data visualization and load the GDT file. The open pores are ID1. We could, of course, change the color of ID1 and turn it visible. And we see, okay, all open pores, yeah, are rather boring. The interesting part, oh, let's change the pore space to white. The interesting part are the green, the closed pores. We can disable the struts, the visibility of the struts. We see, okay, we have in fact some closed pores floating in the structure, or not floating in the structure, enclosed in the struts itself. Let's turn the struts on again and select structure and clip through Z direction. And we see here we have enclosed pores, and here. Or here we have an enclosed pore. It is important to note that the pore size distribution of the open pores might be different from the pore size distribution of all pores. That was the pore space analysis. Next, we will go to the physical properties. And if at one point you have your structure lying very odd, it's very small, or you moved it somewhere where you can't find it, you can always go to camera and click reset view, and it's in the standard reset. The first physical property we are going to predict is selecting predict and FlowDict. So we are looking at the permeability. For that we are doing a fluid flow simulation. In this example we use the Stokes-Brinkmann. Geodict has different flow analysis. The other is the Navier-Stokes. You have to be careful for faster. The word fast is rather unprecise. Often Stokes analysis is enough, but sometimes for fast velocities you have to do Navier-Stokes, which is more complex. And for this example we use the Stokes flow. We click Edit. We already have a warning, no fluid in geometry. We select as pore, we go to air and click OK. Again, we click on pore or the material we now want to change. The material selector opens and you can select one of those. For the permeability, it's important that you select a fluid, in this case air. And you can also see, oh, we have those closed pores inside. So we have to cancel and again load the digital segmented structure and go back to Edit. And we again have to set the pore to air. Now we go to the boundary conditions. We select X, Y and Z direction. This will do a fluid simulation in X, Y and Z direction and computes the full permeability tensor. As I previously said, we would have to take the symmetric boundary conditions. But Geodict has the options for fluid flow simulation that you can use periodic boundary conditions and add an implicit in and outflow. So Geodict adds empty space at the top and the bottom of the structure and simulates through it. This will get rid of symmetric boundary effects, and afterwards in the post-processing Geodict just crops this region out and can calculate the values out. But in tangential direction we have to choose symmetric boundary conditions. In the solver tab we stay for the Lias solver, and important for this workshop, please use for parallelization, click Edit and use the local maximum. It's the default, but make sure to make the local maximum that you can keep up to this workshop. I for myself will use 4 cores in case somebody out here has also 4 threads and therefore might be slower, so that he is not falling behind. Everyone else, please use local maximum. I will use this 4. And one additional interesting thing is Geodict has this equation reference tab. So if you're interested in the theory behind FlowDict module, you can look at the equations, variables and constants and references. We click OK and run the fluid flow simulation. In Geodict, when a simulation or analysis is running, you get this window. You can here additionally expand it to get a more detailed view of what iteration is currently happening. You have a progress bar which indicates how far the simulation is done. Additionally, you can decide to cancel the simulation, which will cancel it and you will get no results. If you will click stop, the simulation is stopped at this specific point and the results are evaluated up to this point where you stopped. And for everyone who is using a floating license and who is sharing this license with your colleagues, if you set up a simulation which is taking maybe 3 days on a very large structure, 2000 times 2000 times 2000 voxels, you can start the simulation and then select release floaters. This will release all floaters except the FlowDict floaters, so that the license is free for your colleagues to use while the simulation is running for you. In the result viewer, we get the permeability tensor in X, Y and Z direction. So we see the permeabilities in X, Y and Z direction. And we also see the average flow velocity the Rayleigh numbers, and the flow resistivity for X, Y, and Z direction. We also have plots for layered pressures, for velocities along the slices, and we can visualize the flow by clicking Flow Visualization. We load the flow from the Y direction, since the Y direction is the long direction, the interesting one, and click Load and OK. In this case, we have several volume fields. So we have all of them listed all here, and you can select which volume field you would like to look at, and by double-clicking, load it. Again, we can disable the structure view. We can crop the structure, and in volume field, we can clip through the values. For flow simulations, another interesting visualization is disabling the volume field view and enabling the streamlines, which are showing the streamlines of the flow through the structure. Again, you can crop through the structure to have a better look at the streamlines, and you can also crop through the streamlines. Next, we are going to look at the tortuosities. For that, we use the GeoApp Compute Tortuosity. We click on Edit, and for the sake of the runtime, we will not compute every possible option. This app computes the tortuosity in various different ways. We look again in the Y direction. The boundary conditions we set to symmetric. We check Compute Geometric Tortuosity and select the first option. We use the Physical Tortuosity and select the first option. We select the Mixed Tortuosity and select the first option. But now we select the second option at this point. For microstructure characteristics, again we select the first. We click OK and run. This will start various geodetic simulations and analysis and extract the tortuosities from them. For example, from a diffusion you can extract tortuosities, and you can extract tortuosities by analyzing the percolation path. You have seen the percolation path before and how it was going through the structure on very different ways. And when this is finished, you will get again a result file which shows you the different tortuosity results. In this tortuosity app, we see the different kinds of tortuosities explained in the beginning, physical tortuosities or deriving from streamlines or from particle diffusion, and the final tortuosity values, the geodesic tortuosity for example, or the blast diffusion tortuosity. Those tortuosities we did not compute are indicated by not applicable, NA. We are looking at predict, conductodict. We are going to analyze the thermal conductivity of this metal foam. You could also do an electric conductivity analysis, but we will do the thermal conductivity for this workshop. Setting up thermal and electric conductivity are almost the same. We go for the thermal conductivity and we click Edit. We now have to define the material because the materials have different thermal conductivities. For example, the air from the database has a thermal conductivity of 0.0257 watts per millikelvins. For the second material, we click on this material of ID 1, and from our database we select aluminium. Since this was an aluminum foam. We now go to the boundary conditions. Again, we compute the conductivity in X, Y, and Z direction, but have to use symmetric boundary conditions in direction and boundary conditions in tangential directions, also symmetric. Then we go to the solver and select the Lear solver. For parallelization, please you all choose your maximum. I choose 4 to make sure that no one falls behind. Everyone else, please choose local maximum. Again, you have equations and references. We click OK and run. If you think, oh, I do not want to see these numbers anymore, you can just click those arrows and hide those additional infos. But I like to see them because they show me how far the solver is done if you have watched a few simulations being done. Again, this might take 2 to 3 minutes depending on your computer. On the progress bar, we can now see that the first third is done. So the first direction, the X direction, the thermal conductivity was computed successfully. The Y and Z direction will take about the same time. So in the end, we might need 3 minutes to have everything done. And that was the Y direction. And now comes the last direction. And again, we are finished in under 2 minutes. As always, the result viewer opens, and as a result, we see the thermal conductivity in X, Y, and Z direction, and we again see that we have an anisotropic behavior of our foam. We also see the runtimes for each direction. Now we go to data visualization and load the volume field in Y direction, because again, this is the longest direction, so the most interesting one. No, the structure should not be turned to invisible. And we see the volume field of the temperature through the structure. Again, we can clip through it. We can disable the structure view. And we can always change to 2D view, change the plane on which we are looking, and slice through it. And last but not least, we are looking at the, just look at the structure again, we are looking at the elastic properties. So for that we go to Predict and choose Elastodict. Now we go for the effective stiffness, the FeelMath Vox, and click Edit. Since we set the materials to be air and aluminum in the thermal conductivity, we do not need to set them again. We now switch to load case, and we do all 6 load cases, but use symmetric boundary conditions. We go to the solver. Parallelization, please choose your maximum. Use downsampling and select 3. In output, you do not choose change anything, and in post-processing 2. You click OK and run. This simulation now it might take 3 to 5 minutes. We wait for it to finish for this part, and then the second part is finished. Again, you can now go get your second refreshing break, and we will meet again in 10 minutes.